Okay, everybody, we're going to go ahead and continue with things about graphs, our chapter 3 with continuity and end behavior. So this part 1 video is all about continuous continuity, and then part 2 will be all about end behavior, what that means. So we're going to jump right in. So these are two definitions I think that you should be familiar with here. So we'll kind of walk these through one at a time. A continuous graph means you can draw the entire graph without lifting your pen or pencil. So it means there's no breaks in the graph, nothing that we would have any open spaces. So we talked about continuous and discontinuous before when we did those piecewise graphs. We'll be looking at those again. So discontinuous then means that there are breaks. You can't draw that entire graph without having an issue. You're going to have to lift your pen or pencil, so we can't draw the whole thing. So what we're going to really focus in on today is what kinds of ways can you be discontinuous? So how can you have discontinuity in your graph? What types there are, and how do you find them? How do you know? And then being able to prove a graph is continuous. So let's talk about the three different types here. So the three different types of discontinuity. The first one is called an infinite discontinuity. These are the ones that have asymptotes in there. So a great example of an infinite discontinuity would be like the parent graph 1 over x. So when you look at the graph 1 over x, there's a place of discontinuity at 0 because x can't be 0, and you have your graph that looks something like this. So infinite discontinuity is an asymptote. Second kind of discontinuity is called a jump discontinuity. A great example of a jump discontinuity, if you think about your parent graphs, would be this one, greatest integer. That's where you have all those cute little steps. So it's going up. So we have all these little steps, and it's jumping up to a new value. So each of those, when you jump up, you have a place where it's discontinuous. So it's changing the y value, jumping up to a new value. And the last type is called a point discontinuity. We're going to talk a lot about these, the difference between especially infinite and point. Some other words to jot down: removable or hole. There's a hole in the graph, or just a single point or location where there is an issue. So we're going to really talk about how do you tell between these three different types if a graph has them. All right, so let's take a look at the three examples that you see on the next slide here. There's three different types, or three different illustrations of those discontinuities. So the first one has this first type of discontinuity we're talking about. It has an infinite discontinuity. So we'll go ahead and kind of label these here. We graphed this one already, that 1 over x squared, that funnel or volcano shaped graph when we were doing inverses. There's a definite issue at the graph because look at the domain. You can't put in a 0, right? So x can't be equal to 0. That excluded value of the domain is telling us something about where the asymptotes are. So that's an infinite discontinuity. Take a look at the middle picture. If you trace it, definitely discontinuous. You trace it down, it looks like it's going to a y value of 1, and then look what happens. You have to jump down to 0 to be able to trace the rest of it. That's called a jump discontinuity. So your y value jumps from one value to another. The last one, if you trace it, you're fine except for just this hole, and then you continue to trace. So when you think about that picture, there's fine everywhere except for that one point where you have an issue. So this would be a point discontinuity. If you look back at the equation, take a look at the excluded value. X cannot be equal to -1, right? That would be excluded. That's why we have a hole there. But the interesting thing is when you look at these graphs, look at the first one and the third one again. When the first one had an undefined place at 0, it left a vertical asymptote, an infinite one. This one had a discontinuity at -1, it left a hole. So why is one leaving a vertical asymptote when it was excluded, and the other one is leaving a point? It goes back to the equation. So take a look at that equation, x squared minus 1 over x plus 1. You can actually factor the numerator. So x plus 1, x minus 1. And look what you can do to simplify that fraction. You can remove the factor, x plus 1, which leaves you with just x minus 1. Right now, think about the graph of y equals x minus 1. It's linear with a slope of 1 and a y-intercept at -1. Look at the line that you just graphed. Y-intercept at -1, up 1 over 1. This red line is exactly what you have left there, that x minus 1. And look what happened at the point. That was something you could remove, right? I divided out the x plus 1s. That was a removable discontinuity then, meaning you don't still have an asymptote. If you can't remove it, look at this one. Can you remove the x? Well, no, there's no common factor. You're stuck with it. So if you can't remove the factor, you are left with an infinite discontinuity. You're left with a vertical asymptote. If you can remove it like we did in number 3, then you're left with the whole. So we're going to be spending a lot of time making sure you can tell the difference between those two things. Okay, so let's talk about how do you prove these things are continuous then? What if they don't have any of those 3 things? So that brings us to something called the continuity test. This is a really big idea. We're going to be spending a lot of time on that again next year in calculus, something being continuous. So the continuity test has 3 different steps that you have to prove and articulate justification for saying that it's continuous. So they're going to use this variable C to stand for the number you're checking continuity at. So when you think about continuity and continuous, you can check it anywhere on the domain of the function. So we can look at any value and see if it's continuous there. So C is standing for constant. It's just standing for a number. So is it continuous at 7? Or is it continuous at -5? You're checking those different values. Okay, so step number 1, the function you're checking to see if it's defined at C. What does that mean? It means it exists. You can plug that number C, whatever it is, into the equation and it's okay. It's part of the domain. So step number 1. All right, so step number 1, does it exist? So does f of C exist? All right, so what that's really asking is it in the domain of the function? So the justification, the work for this to prove it is you have to list the domain of the function. So what is the domain? If C is in the domain, it exists. So that's step number 1. Okay, step number 2, kind of color code a little bit. The function approaches the same y value on the left and the right side of the value of C. Well, what does that mean? Approaches. So when we look at our picture here, if we trace from the left and we trace from the right, we're getting closer and closer to the same value. We're approaching the same location. So what you're trying to avoid is one of these jump discontinuities where you're approaching 2 different numbers. We want to approach the same number. So that's what that's talking about. So I'm going to write it like this. Y approaches, I'm just going to make a box for like a fill in the blank, what number? Y approaches that number from both sides. All right, step number 3. Not only does it approach, so as it gets closer and closer, it actually is f of C. It equals that number. So the 3rd step in your continuity test is that f of C is actually equal to, I'm using the same box as I did number 2, that's the same number that you'd fill in. It actually equals that value. Not only does it approach it, it equals it. So step number 1, does it exist? That's your domain. Step number 2, does it approach the same number from both sides? And then step number 3 is, does it equal that number? So we're going to walk through a few examples to look at how that plays out. All right, so first one, think about the function that I'm giving you. F of x equals 3x squared plus 7. That's a parabola, right? So when you think about a parabola, would it be continuous everywhere at its domain? For sure. You can draw a parabola without lifting a pen or pencil, right? So we have this basic shape. So it doesn't even really matter where I'm asking you continuity at. It's a continuous function everywhere. So is it going to be continuous at x equals 1? Short answer is absolutely yes. Okay, so now it's just the justification. How do we show it? Okay, so step number 1, is f of 1 defined? Does it exist? Well, it sure does, because the domain of your function, if it's a parabola, is all real numbers. You can write it with the R, you can write it with interval notation as well, which will be used again in this part 2. So it definitely exists because it's in the domain of the function, because everything, the domain of a parabola is all real numbers. Okay, I'm going to go ahead and write out step number 2. Since I know it's continuous, I know I'm going to have to do both of these. So I go ahead and write them out. So y approaches the same number from both sides. And then step number 3 is f of 1 actually equals whatever that number is. Okay, so I'm going to go ahead and take a look at what the graph looks like. So I'm going to go to my graphing calculator here, and you guys go ahead and do that too. So go ahead and type it in, 3x squared plus 7. And for my window, I know I'm going to have to see a little bit more at the top of this graph, so I'm going to go ahead and change my y max to 20 just so I can see the top and see what that graph looks like. Okay, so now when I look at my picture, when I look at this picture, I want to be able to talk about what is it approaching and what is it equal. So if I just go ahead and put the value of 1 into the equation, so 3 times 1 squared plus 7, or look in my table and see what it is at 1, it looks like it's supposed to be equal to 10. So I can go ahead and fill that in. It's supposed to be 10. Now, if you think about what is it approaching and you go back to your graph, we can trace on our graph. So go ahead and press trace and see what values it gets closer to as x approaches 1. What is the y doing? So go ahead and look at the bottom of your screen. As x gets closer and closer to 1, so watch your x value change, the y values get closer and closer to 10 from the left. Okay, now I'm going to arrow all the way up to around x equals 2. So go ahead and do that. Now I'm going to come back towards x equals 1 from the right. So watch what the y's do then. As I get closer and closer to 1 for the x's, see how the y's are going down, going down, going down. As I get closer and closer to 1, sure looks like my y's are getting closer and closer to 10. So it's approaching the same number from both sides, that 10. So that's what we're talking about. There's no jump discontinuity there, in other words. It's approaching the same number that it equals. So it exists, it approaches that same number 10 from both sides, and it's equal. So is it continuous? Yes, this function is continuous at x equals 1 because it's continuous everywhere. All right, let's try another one. All right, take a look at this example. We're going to have a few more issues in this one because if you look at the equation, we have a fraction, and immediately I'm going to be thinking excluded values. If you want to figure out the domain, remember you set that denominator equal to 0, and what would those solutions be? Well, plus or minus 2. So that means we're going to have issues. This graph is going to be discontinuous at those places. All right, so look at where the value I'm asking you to check at, x equals 2. So we're going to have a problem. So step number 1, is f of 2 defined? Does it exist? Well, no, you can't put 2 in there because it's going to make the bottom 0. That's not a real number. So I'm going to say D N E, just like Mean Girls. The limit does not exist, right? We can't put that number in there. That's what DNE stands for. Does not exist. Okay, so what's our proof of that? How do we know? Well, the domain of this function is all real numbers, but x can't be equal to plus or minus 2. It's not in the domain of the function. So the short answer to this question is no, it is not continuous. So this graph is going to be discontinuous at x equals 2, which is where they were asking me for. It would also be discontinuous at negative 2. What I'd like you to be able to figure out, though, is what kind of discontinuity is it. So we're going to go ahead and graph this. So if you want to go back and go ahead and put this in. So x minus 2 divided by, make sure you use parentheses or use your fraction capabilities there. Oops, then I forgot to use my parentheses. All right, so parenthesis and then x squared minus 4. Oh, why is it not letting me do that? Oh, that's because I put it in there twice. Good grief. All right, now I think I'm going to have it. Delete. I can't get up into the squared there. Oh, shoot. Start over. Sorry about that. So I have to just get this in here. Go ahead and type it in yourself, too. Hopefully you're doing a better job at it than I am. All right, parenthesis, x squared minus 4. All right, when you take a look at the graph, I'm going to go back to Zoom 6, my standard graph, standard negative 10 to 10. Definitely looks like I'm having issues. Go ahead and make a sketch of this. Look at where your vertical asymptote is. Looks like it's at negative 2. That's an infinite discontinuity, so I'm going to go ahead and make a sketch here. So it looks like I'm having an infinite discontinuity at negative 2. Which is one of those excluded values, and the graph looks something like this. Okay, now I already knew that I was going to have trouble at 2 and negative 2, and so it's pretty clear on the graph that negative 2 is an infinite discontinuity. So that one is an infinite discontinuity at x equals negative 2. What I'm worried about, though, is what's happening at positive 2. If you look at the graph, it doesn't look like there's any kind of infinite discontinuity happening at 2. And it certainly doesn't look like it's jumping, which only leaves one option left. It looks like it's going to have to be a point. Well, how could I see that on my graphing calculator? If you go to your table, it definitely says error there, so I know it's a discontinuity. So it's going to be a point discontinuity, but it's hard to see. You really can't see that on the graph unless you super zoom in. You might be able to see just a little bit of a break between the pixels. So we need a better method. So let's look at the equation. I think we're going to be able to tell from there. So look at the equation and go ahead and factor the bottom. So x minus 2, x plus 2. And take a look and see what happens when you do your simplifying. I can remove or reduce that factor of x minus 1, which leaves me with 1 over x plus 2. Take a look at your graph for a second. Doesn't that look like the parent graph of 1 over x? And what does a plus 2 do to your graph? Well, it moves it to the left 2, which is exactly what happened in that graph. But look what happened to the x minus 2. That was what we call a removable, we removed it, a removable discontinuity. That means it's a point discontinuity at x equals 2. So if you can factor it out, it only leaves an open circle. So go back and make an adjustment in your picture here. You have an open circle at x equals 2. That's a point discontinuity because I could remove it. Why do we still have an infinite one then at negative 2? Well, you can't get rid of this x plus 2. You can't factor it out. You can't reduce it. You can't divide it. You're stuck with an infinite discontinuity there. So asymptotes are stuck there if you can't reduce. So we had two different discontinuities in this one. We had a point and we had an infinite. Okay, for our next couple, we're going to do some of these piecewise graphs. So what I'm going to ask you to do is go ahead and graph this and then start the video again so you can take a look and see what's happening. Okay, so our piece number 1 for the graph is 1 over x, and it's not equal to, we're starting at, not equal to, let me circle that so it doesn't look that way. So all the x's that are greater than 1, not equal to, so open circle at 1, 1, and then we have a point at 2, 1/2, and we get this little branch part of 1 over x. So think of what the whole parent graph would look like. It would just be that piece. Piece number 2, y equals x, that's the identity graph. It's y, or x is less than or equal to, so it's going to be a closed dot at 1. So that open circle gets filled in, and then 0, 0, and on down that line. So take a look at the whole picture. The graph is continuous everywhere. When you look at that graph, you could trace the entire thing without lifting your pen or pencil. The one place we were concerned about was at x equals 1, and that dot got filled in, so we're good. So we know this graph. The short answer is yes, it's continuous. All right, they want us to check at x equals 1. Is it continuous there? Well, sure it is. So we just have to go through those 3 steps. So step number 1 is f of 1 defined? Does it exist? Well, sure it does. What's our proof? We have to say our domain. Well, what's the domain of that function? All real numbers. If you do all the x's that are greater than 1 together with the ones that are less than or equal to 1, you've got everything. So it exists. Step number 2 and step number 3, I'm going to write them both out here. Y approaches what from both sides? And then step number 3 is f of 1 equals whatever that number is, that same thing that it's approaching. So let's go ahead and kind of fill those both in at the same time. What does f of 1 equal? You can look in your tables. F of 1 is equaling 1, right? When we put in 1, we get a 1. And what does y approach from both sides? Well, if you trace along the graph from the left and you trace along the graph from the right, looks like we're both approaching the same value, and it looks like they're both approaching a y value of 1. So not only does it equal 1, it approaches it. So this one is definitely continuous at x equals 1. So it existed, it approached the same number from both sides, and it's equal. Okay, we're going to finish up with our last example here on piecewise. So go ahead and get this graph. So go ahead and pause the video, get it graphed, and then we'll talk about what happens. All right, so here's our piecewise graph here. So piece number 1, piece number 2. Make sure you double check the graphs, and that makes sense, the open and closed circle. So when you look at this graph, not continuous everywhere. There's one place we have an issue, and where is that x value that we're having a problem? Looks like it's at 2. Okay, so at x equals 2, this is a discontinuity, and the type of discontinuity we're dealing with is jump. So it's a jump discontinuity at x equals positive 2. So everywhere else in the domain, if I ask you negative 7, positive 12, 50 million, if I ask you is it continuous there, yep, it sure is. But at 2, we have an issue. So that's the x value that I want you to check. Is this graph continuous at 2 so we know how to write this out? So the short answer to the question is definitely no. So in a piecewise one, we should be able to see that pretty quickly. Let's go through the steps. So step number 1 is okay. Is f of 2 defined? Does it exist? Well, sure it does. Because again, you have to say the domain, that's your justification, is all real numbers. If you take all the x's bigger than 2 together with less than or equal to 2, that's everything. Okay, here's our issue. It happens at step number 2. Y approaches what? Okay, so we're going to go from 2 directions here. So we're going to go from the left first. If I come from the left and I trace down my graph, it looks like y is getting closer and closer to the x-axis there, so 0 from the left. All right, well, what happens from the right? So y approaches what from the right? If I trace from the right, closer and closer and closer to x equals 2, it looks like my y is approaching 4 from the right. And that's our problem. You can't approach 2 different values and be continuous. So because of those 2 things, together, that's why we have a jump discontinuity. It's approaching 2 different numbers. It's not approaching the same y, so it is discontinuous. And you can stop there. In a continuity test, as soon as you prove the discontinuity, that's all you need to do. So for that one, that's as far as I'd have to go. So continuity, there's 3 different types: infinite, jump, and point. 3 different steps to that continuity test. Does it exist? Check the domain. Does it approach the same number from both sides? And does it actually equal it? All right, so that's our part number 1. That's the assignment. And part 2 will be on end behavior.